Okay, so I will be talking about actin and actin's role in the sliding filament theory. I have this picture printed off to help better explain some things. So up here at the top is actin, and down here is myosin. Actin's also called the thin filament, so if I ever say thin filament, actin. You can see that actin kind of looks like two strands of pearl necklaces, but twisted around each other. This myosin head right here will actually attach to different parts of the actin, and it will tug on and pull the actin across the myosin, and that gives us the power stroke, they call it, and that's what gives us the contraction that we see in any muscle.
I will be talking about myosin's role in the sliding filament theory. So first, myosin will bind to the actin, and then the myosin will alter its configuration, resulting in a stroke that pulls the actin filament and causes it to slide across the myosin filament. And so down here is the myosin, and up here is the actin, which the myosin will bind to and pull it across, resulting in that muscle contraction. And the breakdown of ATP releases energy, which allows the myosin to pull the actin filaments inward, causing the muscle to shorten. This will occur the entire length of each myofibril in the muscle. Then the myosin detaches from the actin, and the cross bridge is broken when the ATP molecules bind from the myosin head.
So I'm going to be talking about the Z-disc portion of the sliding filament theory. Here is a Z-disc, and here is a Z-disc. Z-discs are on the ends of sarcomeres, so this whole thing is a sarcomere, Z-disc on each end. Z-discs are actually specialized proteins that act as anchors for actin and myosin filaments. So during the power stroke, this is a relaxed sarcomere versus contracted, it all shortens. So during the power stroke, when the actin filaments slide into the midline, as you can see here, the whole thing shortens, the whole sarcomere. And when that happens, the Z-discs get closer together, and that's the power stroke. So now I'm going to be talking about tropomyosin. So here you can see these round balls, these are actin, and the little dots in the middle of them are the myosin-actin binding sites. Tropomyosin is actually a thread-like protein. You see here, it's kind of like a string, and it covers parts of actin. Specifically, it's covering these binding sites. So actin and myosin can't bind here in the relaxed state, but when calcium binds to troponin, since troponin and tropomyosin are bound together, this will cause tropomyosin to move away from these binding sites.
Today I'm going to be talking about troponin and its role in the sliding filament theory. And I have this little picture to help kind of give a visual aid throughout what troponin does. So troponin, being this little red dot here, it'll bind to calcium, and then it'll bind to tropomyosin, which is this black line. And from that, these little black dots underneath of it are the myosin heads. And when troponin binds to tropomyosin, it frees up the myosin heads, allowing the actin to bind to the myosin, which allows for cross bridge formation. And with the cross bridge formation, it allows for muscle contraction to occur.